This podcast is brought to you by LMU Munich.
I should first give a plan to point out that there is a missing gap somehow. There's a Barbour-type 1982, some of which is in this talk, and Harvey mentioned that. There is then Julian's work on geometric dynamics proper. Then there's conformal geometric dynamics, which I think is most of what Sean will be talking about. And in both of these approaches there's emergent time. And then also there's timelessness, which featured in one of his papers from '94 and in the book The End of Time. Okay, so between Sean and I and Harvey, we're going to cover that and that and that and that, but not this one. So you shouldn't forget that there's actually non-conformal ordinary formulation of geometric dynamics as well. It's just that nobody's talking about it, but there is that. I'll only have a couple of slides about timelessness myself, but I will include it in this talk. Okay. So Julian Barbour set up a theory of relational particle mechanics in 1982 with Bertotti, and in this one scale still plays a role, and he set up another theory of mechanics in 2003 where overall scale does not play a role anymore, so it's a theory of pure shape. And these are in some sense the antecedents of ordinary geometric dynamics and conformal geometric dynamics, where there's a different notion of scale, a local notion of scale that's taken out in the latter but not the former. Okay. Given those theories of mechanics, one fairly sensible question to ask is what are their configuration space geometries? And I started working on that from first principles in the early 2000s. But then I found that Kendall, who was a geometer and a statistician, had already worked out a shape geometry which turned out to be exactly the same one that was needed for Julian's theories. So they were both thinking about shape in exactly the same way, despite working in entirely different fields. Statistics and pure mathematics on the one hand versus mechanics and wishes to apply mechanical ideas to theoretical physics in the other. So it's quite satisfying that this notion of shape has come up in two different fields, and also that's allowed for cross-checks to make it very likely that it's correct. Okay. Kendall's shape geometry covers the pure shape theory, but it turns out there's a very simple construction called making the cone, which you can do to Kendall's shape spaces to make the shape and scale spaces of Barbour-type theory. So the Kendall case and a trivial construct suffices to get the configuration spaces for both of those theories. And then there's two ways one could get at it. One could reduce those theories that Julian wrote down by getting rid of the auxiliary variables in them, or one could perform Jacobi-Singh's construction, which allows for a theory of geometry to be turned into a theory of mechanics, where the geometry is now the geometry of the configuration space, so it features in the kinetic part of the structure of the theory. And then there's an analogy between general relativity and these relational particle models, which has many aspects. I listed something like 120 similarities between these in my review of this subject, although there's about 30 or 40 differences as well. Mechanics can only be taken so far. In particular, the problem of time plagues attempting to quantize general relativity, and it has a number of different facets, and it turns out that these relational particle mechanics models already contain 6/8 of the types of problem of time, although here they're quite a lot easier to resolve. So my review goes on to resolve those in dimension 1 and 2, which suffices for the analogy between GR and relational particle mechanics models. So to me, relational particle mechanics models are not a model for the 3D universe, but a 1 and 2D toy model that has about 120 similarities with GR's geometric dynamics. Okay. And that's work that I already did in the mid-2000s. The newer work that I'm presenting today concerns how Kendall's further application to shape statistics can be used to set up a classical version of a timeless records approach, like the one in Barbour's timeless works from '94 and in The End of Time. Okay, let's have a quick look at what Barbour-type theory looks like, given that we didn't have any slides in the previous talk. This is the way that I like to write it, which is not the original way, but is the most sensible way, I believe. Okay, the action principles are written in a form which doesn't contain any extraneous time-like variables like Newton's time, and by this stage it doesn't include any meaningless time labels either, because although those feature in the original formulation, they cancel out. So it's written as an entirely geometrical theory. You can see this as a geodesic principle, or maybe a parageodesic principle, which allows for it having a conformal factor, the square root of the W, which is the E minus V potential type term that one has in mechanics theories. And having it be of that form implies as a primary constraint, i.e. just as a relation between the momenta without doing any variation, an energy condition like this one. And if one does the same in the case of the geometry dynamics, one gets the GR Hamiltonian constraint this way. So then the way this works, as far as I understand it, is that you start off by postulating there's no time for the universe as a whole, a Leibnizian postulate. You implement that with one of these geometrical actions that happens to make no reference to a label time. And as a result of setting up a theory to be that way, you automatically get an object like the GR Hamiltonian constraint, which is at the core of GR as a dynamical system and is at the core of many of the aspects of the problem of time too. So all these are to be expected because there's to be no time for a universe as a whole already at the classical level. And one resolves this timelessness by Mach's time is to be abstracted from change, which is implemented in this theory by an expression of this form. And you can see that the ds contains all those dq's, which are configurational variables, so the ds is a manifestation of change. And in fact, all the dq's enter the ds, so in principle it's abstracted from all the change in the universe, which is that holistic element, but then in practice many of these dq's can be discarded as irrelevant to the local physics in the final form. Okay, some of these mechanical theories have an extra element, because so far we haven't done anything about things like rotations in absolute space. That was a 1D version or an incomplete version on the previous slide. There's also a group G of irrelevant transformations. And the way one deals with these is introducing auxiliaries. So the Q's already have redundant G's, and then you introduce G's on top of that. That looks like you're making your situation worse by introducing the G's as well. But then when you vary with respect to the G's, they use up 2 degrees of freedom each. The one contained in the G you appended, and the one originally contained in the Q that you didn't want. So this method does indirectly succeed in placing you on the quotient space Q over G as desired. And in the most obvious case, this would be removing the translations and the rotations from one's picture of the world. So then there'd be no reference to absolute space. Okay. And then that ds would now contain these corrections with respect to translations, these dAs and these dB cross QIs to take out the rotations. And if one was doing the dynamics of pure shape, as in Julian's 2003 paper, there would originally be a CDQ here for another auxiliary C, and that amounts to taking out the scale. And then varying with respect to each of A, B and C produces constraints. There's no total momentum for the universe from the translations, no total angular momentum for the universe, and then finally no dilational momentum, this other quantity, which is a dot product version of what an angular momentum was a cross product of. Okay, so those are implemented. Okay, what does Kendall's shape geometry look like, which turns out to be the right geometry for these things? Okay, so we start off with n particles in dimension d. So we have RND, and then we take out the similarity group, i.e. translations, rotations, and dilations. Well, it's very easy to do calculations. You can do these, on the back of an envelope to show that in dimension 1, these things are n-spheres. It takes quite a lot more work, and I'm grateful for Kendall having done this before I came on to looking at it, that the two-dimensional ones are complex projective spaces. And then there's a very simple case, which is the case of 3 particles. That's CP1, and that's well known mathematically to be S2 as well, and S2, the two-sphere, is very well understood space, so there's lots of extra methods available for this particular case. So then what happens is you have the space of all triangles, which are the configurations of this system, and those form an S2, and if they're unlabeled, then, because there's the various ways of labeling the base and the apex, then you only get a piece of the sphere as the fundamental cell. And this is what Kendall called a spherical blackboard. So along here, there's pi by 3's worth of the 2 pi in the sphere, and along this way it's a hemisphere's worth, so it's a sixth of the sphere that you need for the unlabeled case. If the labels are distinguishable, then you need the whole sphere. Okay, and it's set up such that the north pole is the equilateral triangle, and the equator is where you have the collinear configurations. And okay, right, and you can do this for other cases as well. I geometrized the case of 4 particles in the shape of the axe that isolates the three-dimensional 3-particle subsystem as the blade of the axe, and then I have a CP2 chopping board equivalent of that. The point about spaces like this is that one can draw the dynamical trajectories on them and just read off from what triangles are on the thing, what sequence of triangles the dynamics goes through, and then you can do the same when it's a quantum wave function and see where it concentrates and where it doesn't just by reading it off the underlying diagram. And likewise, when you do statistical distributions for triangles like Kendall, for purely classical statistical work, then one can just read off this diagram what one has as well. So it's a very, very useful tool, and it allows you to crack all the dynamics, all the quantum mechanics of these things, plus it allows you to investigate various things in the real world that are described by shape statistics, as we'll come on to. Okay, in the scaled case, you quotient out by the Euclidean group, so only translations and rotations. And now, as I said, it gives the cone over what one had before, and the cone is the obvious construction when it's for a circle, but it's allowed for any space now. So you let that space exist and have all possible sizes, and they're all there together, so it's cross and R+, and then you have to stick on an extra special point, the apex in each case, which is already true for the simple notion of cone, but continues to be true here too. That's the topological definition of a cone. The metric definition of the cone is simply a line element like this related to the original geometries, which is a very simple form. And I should say that in Kendall's work it was demonstrated not only that the one-dimensional shape spaces for these things have spheres with a spherical metric on them, but the CPNs have a metric that's natural for them too, known as the Fubini-Studi metric. That's the simplest metric that one can imagine on these CPN-2s, so it's very natural from a mathematical point of view. Okay, let's have a look at how you do the reduction. This requires going through various coordinate systems, but you don't just change the coordinates, you have to at each stage remove auxiliary variables, that A, that B, that C, and you have to manipulate the actions so that they're written in terms of these. But one moves from particle position coordinates, which are relative to an absolute origin, the O, absolute axes in pink, and the absolute scale, the yellow ruler. You pass from these to interparticle separations. In fact, it's advantageous to use interparticle cluster separation, so-called Jacobi vectors, so then they're the red arrow along the base and the red arrow along the median. But those still refer to the absolute axes and the absolute scale. They've only got rid of the absolute origin. However, if you take the magnitudes of those two and the relative angle between them, then you see there's no reference then to the absolute axes, so they're absent from the third figure. And if you want to get rid of the ruler then, well, you consider the ratio of the median to the base and use that as a variable, or in fact the arctan function like so. If you use the arctan function like so, then that relative angle variable and this new variable you've defined in terms of the ratio, then the actual spherical polars on Kendall's spherical blackboard. Okay, and there's a few more useful coordinate systems for these. In the scale case, then you'll be wanting, well, they're mass-weighted Jacobi vectors. So the natural scale, in fact, is the square root of the moment of inertia for the system. And then one can normalize the coordinates with respect to that. That's what the ends are. And then in yellow, there are some nice combinations that turn out to be the coordinates for the surrounding Cartesian R3's axes, which are a measure of anisotropy, of area, and of ellipticity, which means the difference between the partial moments of inertia of the system, essentially. Okay? And if you stuff all these things in the action, starting off with Barbour's one from 2003, you end up with something which contains that Fubini-Studi metric in the two-dimensional case. Okay, and these are, so the simplest triangle case, but you can repeat this procedure for n particles in 2D, that can be done as well, it just takes more space to express. And if you set up a theory of mechanics on this geometry, you get exactly the same thing. And I should say at this point that this is not obvious, because other people apart from Kendall also suggested shape geometries, and theirs are not the same as Barbour's configuration spaces. And that's because they conceived a shape in different ways. There was somebody called Bookstein who set up a shape geometry which made it impossible for things to be crushed down to zero size. So then he was ascribing some kind of material property to the triangle or entagon itself. Whereas in Julian's case, it's only the particles that really count, so there's nothing wrong with them all being aligned, which amounts to a zero size, a zero area configuration. So if you tried setting up a Jacobi Singh for that thing, for that geometry of Bookstein's, you'd get a different answer from this and you get a different theory, but it wouldn't correspond to the carefully thought out notions of a relationalist mechanics that Julian set up. So whilst for entirely different reasons, Kendall and Julian were thinking exactly the same about this simple notion of shape. Okay, now let's look at a timeless approach. Or what records are in general. This is a separate chunk of material. Okay, so there's the Hamiltonian constraint in GR, and that produces the frozen equation here, the h hat phi equals 0, rather than some IH bar d by d of some notion of time of the wave function, which is what you'd expect for an unfrozen equation. So the quantum general relativity looks frozen. Okay, one attitude that one can take to this is implemented at face value. If the equation says it's timeless, then let it be timeless and then see what physics you can do with timeless. Alternatively, you can, for instance, apply a semi-classical approximation to that equation and then obtain an emergent semi-classical time from that. Or you can ditch the whole thing and start conceptualizing in histories and approach it that way. So there's different ways that one can do it. You don't have to take them at face value. But if you do take it at face value, then one way of dealing with it is called records theory. Although there's also a records theory that occurs within histories theory, which is not a timeless records, but a records within histories approach. So records theory has more uses than just the purely timeless one. So how can one conceive of a record? Well, different people have done so in different ways, but the ones that I believe in are information containing subconfigurations of a single instant, and they're localized in space and in configuration space, and they additionally contain useful information. That means within that one instant, there are correlations between the physical entities. And then these form some kind of pattern if there's a meaningful record there. And then if one's theorizing is timeless, one has to hope that what patterns one finds in these timeless correlations can be used to abstract a semblance of dynamics or of history. On the other hand, if your records theory lives within a presupposed histories theory, you don't have to apply this last step. So life is easy for you, and a records theory is simply about subconfigurations and about pattern recognition. And this last step, it's never really been established how to do it with any great degree of accuracy. And I'm not going to claim that I believe in it either. I prefer versions with histories, at least for the past few years I have. Okay, so now let's have a look at how to make statistics relational. Here's some very basic statistics. Correlation coefficient of Pearson. Is it relational? Well, it's scale invariant because it has the same number of powers of variance and covariance upstairs and downstairs. There's also translation invariant, but it's blatantly not it's very not rotationally invariant, because as you know, if the line of best fit points upwards, the coefficient is positive, and if it points downwards, it's negative, but the two are related by a rotation. Okay, so that notion fails to be properly rotationally relational. However, if one inspects the covariance matrix and uses the fact that that's a tensor, so that it has invariance within it, and they're the determinant and the trace for this 2D case, then one can build a properly relational invariant out of that, this rho rel, which is related to Pearson's coefficient and to some ratio of variances one way plus ratio of variances the other way. So then one can use that as a statistic that has rotational invariance as well as translational invariance and a scale invariance. And in terms of the shape quantities in the case of the triangle, it adopts this simple formula. And it has to adopt a formula in terms of these because those are a basis for the shape quantities. So all shape quantities for triangles have to be expressible as area and isoscelousness and ellipticity combinations. And it comes out as a particularly simple one in that case. Okay, and that's very simple statistics. We need to do more complicated statistics. Let's take a few notes first of all. Statisticians tell me this relational rho I found is very well known, although its interpretation in terms of shape quantities isn't. It's interesting then to ask what formula would it have in terms of the shape quantities for the general enneagon rather than just the triangle. Also, a function of that statistic will itself still be relational, and that might help with it complying with various other things that statisticians would want it to have to make it a good statistic in other senses. I also comment that the other well-known rows, like for instance Spearman and Wilcoxon's rank test rows, they also fail to be relational, basically because those procedures involve ties, but the notion of whether two things are tied depends on whether you've rotated things or not. Here they're lined up to each other, so they are a tie, but if you twist it round, then they're no longer a tie. So procedures that involve treating ties differently from other things aren't rotationally invariant either. But still, all that statistics is just a relationalized version of schoolboy statistics. Kendall's shape statistics is altogether more subtle. Here you don't probe the correlation in terms of one great line. You ask, do the individual sets of 3 particles in a setup, like say the standing stones of Land's End, which is what those green dots there might represent, is there an unusual number of particularly straight pink lines going through 3 of those that suggest that early man set these up carefully in straight lines? You might look at that diagram and say, well, maybe there's 15 pink lines there. Is that a statistically significant number? Well, Kendall's statistic can be used to test for that particular sort of proposition. It's based on having a critical angle epsilon between 3 things that's very small. And then given a bunch of points, then essentially you're sampling in 3s and seeing above what number of 3s it's no longer random chance, but it's likely some kind of a pattern that was caused by something other than random chance. Okay? And the way this is often done is you let the points lie inside a convex set, and essentially the reason to do that is a box normalization, as is familiar from basic wave theory or quantum mechanics. You're using uniform distributions, so you need them to apply over a finite region in order to be normalized. But there are also distributions that tail off that don't require you having this boundary, which is sometimes natural, the Cornish coastline for the Land's End standing stones, but it's sometimes highly unnatural. That would be some sort of absolutist imprint if it was being done for a relational mechanics. And then also I distinguish between a geometrical statistics, that merely means doing statistics on a manifold, and a shape statistics, which is doing statistics on a manifold, the points of which a fortiori are interpreted as notions of shape in space. Okay, so it's a space of spaces, that spherical blackboard of Kendall's. Each point in it is a triangle, which itself is a shape. And that's something which, of course, the people in the audience who know about GR knows happens there as well. Okay, so there's the shape statistics isn't just a geometrical statistics. It's for a space of spaces. Okay, now, Kendall's is the harder of the two, because there's actually another sort of notion of shape in general. In 1D, in fact, there isn't anything like Kendall's relative angle information. It's all ratios. And in 2D, there's one piece of ratio information for each angle. There are ratios of relative separations as well as relative angles. There's 2 sorts of relative information. And the ratios of relative separations are easier to analyze, are known as clumping, and there are many obvious examples in astrophysics. Galaxy clusters, voids, tight binaries. Okay, test how many of those you have present. Because this is easier to deal with than relative angles. It was done years before Kendall did, for instance, by Roche. He analyzes whether the clumping like this is significant, and he does it with a discretization approach, which essentially is a coarse graining of the physical configurations. Okay, so the idea then is that there are clumping tests, and there are Kendall's extra relative angle tests, and those can be used to determine whether one has a pattern or not in one's configuration, which one can then interpret as one of Julian Barbour's snapshots of a set of particles in this dynamical setting, which is not what these things are usually applied to. I mean, you might study clumping in astrophysics, but the relative angle information, as I showed you, is usually used for something like the standing stones problem, which is, if you like, something in statics rather than dynamics. But it can be used to analyze such configurations nonetheless. And those, of course, are one's notion of localized records. They're a good record if they contain a discernible pattern, i.e. something which is statistically significant according to Roche's clumping tests and Kendall's probing in 3s tests. A few useful, relevant comments as far as relationalism and records go. Well, first of all, in Kendall's test, probing in 3s is probing with a minimal relationally meaningful subsystem. looks good to me. The space of triangles is S2, or a piece of S2 when the labellings are indistinguishable. So obviously it's a sort of geometrical statistics to build distributions on that. Okay, there's never any problem in terms of fitting them inside some convex polygon because it's pure shape, so it doesn't matter what scale the things have. You can always make the polygon bigger. But if the statistic involves the shape of the polygon as regards its detailed outcome, then that's an imprint of the absolute, so it's no good. So you'd much rather not have to put a convex polygon around it and use one of those distributions that tail off instead. That those are entirely relationally compliant. Then, the particular configurations that are picked up by Kendall's test, where the epsilon here is smaller than a certain amount, live near the equator of collinearity within the piece of the S2. And then, let's see. You can't do this just for triangles or quadrilaterals, the sort of things that it's easy to solve the dynamics for, like in the papers I've written so far, because now there's the issue of statistical significance. If there's just a triangle, the sample size sampling in threes is just 1, and a sample size of 1 never allows for statistics. But a sample size of 4, the 4 constituent triangles within a quadrilateral, is also too small for doing statistics with any reasonable accuracy. There is a statistic now, but it's not very good. As you know, in basic statistics, you need a sample size of about 30. And you also might have a problem if your population size is 32. So on the grounds of this, you'd want more than 3 or 4 particles. But if you have about 20 or 30, the number of triangles goes up very quickly. So, okay. So, and the good news is you can solve the energon dynamics classically and quantum mechanically. It's a bit harder, it requires more special functions, but they're still tabulated ones, so it's not a big deal. Give me a couple of years and a bit of money and I can give a full account of how to solve that too. Okay, now let's see. Okay, it's not just a shape geometry, it's obviously a shape statistics because the geometry is of a space of spaces where each of the spaces, the smaller spaces, is a shape. Can one extract a semblance of history from this? Well, to some extent. For instance, if in the Land's End problem, if the epsilon is about 10 degrees, it indicates that people with that particular level of culture that might have set these up were trying pretty hard to set them up in straight lines, so they might have been doing so for astronomical purposes or religious reasons, whereas if the epsilon test is set at about 1 degree, this is fairly rough. So they might just have been used as fences or as indicating roads that needed to be roughly straight. So there's a certain amount of inference that one can get from this, but how much detail, well, I think that at the very best these abstracting dynamics or history from records is an imprecise science unless you've got a vast number of records, which is okay for human history, but it's probably not okay for many aspects of the early universe. Yeah, let's get on to the conclusion. Okay, short conclusion first of all. Shape geometry and shape statistics of Kendall are both useful for having a classical records theory of Barbour's relational particle model, which is a valuable theory from the relational side of the absolute versus relative motion debate. And a simple question is expressing the statistics for these various things, the very simple ones like Spearman's, but also Kendall's in terms of the shape quantities that are particularly meaningful for the dynamical theories. That's an easy question to do, but as I say, it's only been done for the triangle so far. Let's be more vicious now. In general relativity, you have an altogether larger shape space. That one up there, conformal superspace, which will probably enter Sean's talk, more or less. You're now taking the space of Riemannian 3 geometries, as mentioned in Harvey's talk, and you're quotienting out both the 3 diffeos, diff sigma, and the conformal transformations. Okay? This being another space of spaces where the individual smaller spaces are shapes, can we do a shape statistics for this harder case? Okay, now that's a very hard question. None of the statisticians have any idea how to do that. Now let's look at some simpler problems that there are along the way. You might take homogeneous GR, then it's called mini superspace, and at least it's a finite dimensional manifold. You might have a better chance of doing statistics then. On the other hand, there's far fewer notions of shape now. There's only anisotropy. You'd like there to be some inhomogeneity as well. Another way of keeping it easy is working in 2 + 1. Then the equivalent of conformal superspace is a better known, better studied space called type Muller space. Finally, you might consider small perturbations about homogeneous GR. That's harder than either of those 2 examples, but it has the advantage of being what you actually want that's of cosmological relevance in analysing observational data, like say from the Planck satellite. So this work might eventually lead to better statistical methods for examining cosmological data. So it's not completely empty and quaint. I'll end simply with a view of how records theory takes on quite a lot of further flavour in the case where it's applied to a quantum theory. What Barbour postulated was that it was a conjecture that maybe a paradigm for records theory comes from the bubble chamber, where there's alpha tracks moving around. There's alpha particles moving around and they cause tracks to appear, and the tracks appear to be very highly linear. And actually, the physics within the bubble chamber is described entirely by the time-independent Schrödinger equation, so it's a timeless situation. And nevertheless, there appears to be a strong record that indicates a motion happening. So is this time-independent physics producing an apparent dynamics or history, the trajectory of the alpha particle? I should mention that whilst Julian posited that in 1994 in his End of Time book, there is some sort of competing idea by Hughes and Zay. In this one here, something like a dust grain, which is the big green blob, is decohered by smaller things, microwave background photons. And then you have the misfortune that those microwave background photons end up spread all over the microwave background sky. And the inhomogeneities in blue and red, as depicted in typical sort of Kobe pictures or whatever, are unfortunately very small, 1 part in 10 to the -5. So the information about that individual dust grain has ended up scrambled up with the information from all the other individual dust grains and spread over the whole sky. So the basic problem is that there isn't something like a nice track, it's irretrievable. So then one potential problem with this sort of approach at the quantum level in terms of getting any information out at all is that it may be that in nature very few records are actually capable of producing something nice and sharp. And the final conjecture Julian made was that maybe the configuration space has an interesting geometrical shape, and then the probability density function peaks about some particular geometrically privileged place. And furthermore, this place happens to be where the records are present. So on the basis of that, there might be some kind of selection principle for things that look like that track rather than look like this CMB mess. But that remains entirely a conjecture. There's been relatively little evidence against this, and I think no evidence for it. So, it's one for future people to tackle. I'll end just by leaving the set of references visible. Okay.